Here's a little video about substitution in an indefinite integral. In other words, how do we anti-differentiate certain kinds of functions? It's really about undoing the chain rule, which is not always easy, but sometimes it works, and it's a really important technique. Here's a hard problem that someone might give us. It's a very, very hard problem. The integral, or the antiderivative, an indefinite integral, of cosine of x to the fourth plus 1 dx. Okay. Why is that hard? It's because the natural guess would be sine of x to the fourth plus 1, but I can check that by taking the derivative. The derivative of that, it does give me part of what we want, but times 4x cubed. That doesn't appear here. Now, let's see, could we fix that? In some cases, we can fix that by just dividing. Well, let's see. What if I just divide by 4x cubed here? Is that going to be just cosine 4x to the fourth plus 1? No way. This is going to be quotient rule. Okay. If you get a constant popping out, you can undo it after the fact. But here, you just can't do it. Okay. So, this problem actually just really is super hard, to be honest. Let's look at an easier problem. Here's really just a plain easy problem now that we just had the calculation we did. Let's go back to the true guess here. This was x to the fourth plus 1. What was its derivative? It was cosine x to the fourth plus 1, but times 4x cubed. Hey, look. That tells us the integral of 4x cubed cosine x to the fourth plus 1 dx. That is easy. We just found it. It's equal to sine of x to the fourth plus 1 plus c, of course, to be really correct. So the situation here is that we had an outer function and an inner function, the typical situation for a chain rule. The outer function, we knew the antiderivative of just cosine of something, and I'm going to have a name for that something in just a second. That's sine of that thing. And we were so lucky that we were also staring at the derivative of the inner, which is exactly what you get when you take the derivative of sine x to the fourth plus 1. This turns into cosine, and this gets left alone in the middle, inside the parentheses, but then also the 4x cubed pops out. So, this is a little contrived because it's actually set up to be exactly outer and inner, and then derivative of inner. But it turns out that sometimes we can massage things into that form. So, for example, here, 7x cubed cosine x to the fourth plus 1. Okay. Well, you know what? That's the integral of 4x cubed cosine of x to the fourth plus 1 dx times 7/4. And you know what? That 7/4, since it's a constant, that can just be brought out. Times the integral of, hey, voila, it's exactly what we had up here. That we know, because it's outer of inner times derivative of inner. And so that's going to be 7/4 times sine of x to the fourth plus 1 plus c. Okay, now how do we, this is kind of too guess and checky really. How do we rephrase this in a better way? Well, we need a better name for the inner function. Okay, and we're going to do that by saying, well, what we do is we do a substitution. In a way, it's the standard algebraic idea of substitution. If you've got something that you want to kind of hide away for a minute, the basic idea is that we wanted to see this cosine turning into a sine. We didn't really want to worry about the x to the fourth plus 1. Well, let's just try to hide it. Let's just call it u. Okay. I'm going to put a little space in here because there's two things we're going to need in this little sidebar calculation that are crucial. I'm going to make sure I leave space for those. But then what's going to happen? Okay, the integral, this integral here, well, there's some stuff in the front which I'm not going to worry about. The core of the integral is it's really just cosine of u now. Okay. And then I've got this dx. What is that dx doing here? Well, this is where the dx comes into its own. It's a reminder of how to deal with the chain rule. Okay. What we're going to do is we're going to say, remember what the key thing was? It was that if the 4x cubed were there exactly, that would be wonderful. Why was it so nice? Okay. Let me just put this in here. Okay. What is the role of the 4x cubed? It was d by dx of the inner function. Oh wait, I know, I have a name for that. That's du dx. Okay, so in other words, du dx, the derivative of the inner, which was so crucial to have around and available, is 4x cubed. It turns out that it's nicer, the notation works wonderfully well if we write that in differential form. Because look at what this is. Look at what we're staring at here. This was the way that it worked out, sort of ad hoc, guess and check. We looked at the 7x cubed and said, well, that can be written in terms of 4x cubed. What we're going to do is say the 4x cubed times the dx, hey, that's just packaged up as du. Okay, so suppose we hadn't done this calculation before. We don't have to know that at the start. We just say we're going to package up the inner function, which is x to the fourth plus 1, and we're going to take the derivative of that, but we're going to write it in differential notation. And then we're going to try to match that with what we see. So we're still trying to build a new version of this integral. The problem with it so far is that we have this u and an x in it. We never really want to end up with this kind of weird expression. In fact, we probably want to avoid writing mixed expressions at all with u's and x's in them. So instead, what we do is we say, okay, this is going to turn into cosine of u. That's cool. Then I've got a 7x cubed dx. That's almost packageable up as du. But let's just figure out how to package it up a little better. X cubed dx, we just move that over. That's going to be 1/4 times du. Just doing a little algebra, moving the fourth over. And so 7x cubed dx, which is what we actually need to match, is, just like emulating what's going on up here, 7/4 du. So the du is just basically a name for this derivative of inner. And the way the differential notation works out is that dx is always hanging out there as a reminder to do this kind of calculation. But it really isn't anything more than anything different from what we were doing here. Realizing that 7x cubed is very, very similar to this amazing thing that we'd love to have in this expression, the derivative of x to the fourth plus 1. Okay. Now we're ready to rock and roll. Because 7x cubed dx is everything else that we see in this expression besides cosine of x to the fourth plus 1. So it turns into cosine u and then just times 7/4 du. And that, the 7/4 comes out, and that's the integral of cosine u du. And the miracle here is that the x has gone away, the x to the fourth plus 1 has gone away. We're looking at a brand new integral, and we know how to do that. Cosine, it's just the antiderivative of cosine. So that's going to be 7/4 sine u plus e. Cool. And then the only thing we have to do at the end is to realize, hey, we made this abbreviation. This substitution, u equals x to the fourth plus 1, was designed to try to get that complexity out of there. We just have to be honest and put it back in at the end. Okay, so that's kind of why the method works, is it's emulating this, it's kind of making a very slick method for emulating the guess and check here. Okay, so let's just do one more problem where we do it the right way from the start. Okay, so we're going to do the integral of, let's say, cosecant squared x times e to the cotangent. Let's say e to the 2 cotangent x dx. Okay. So what we want to look for is, we're going to make a sidebar calculation. We want to look for an outer function and an inner function. There's two pieces of this. There's the cosecant squared, and there's the e to the 2 cotangent x. The more complicated part of the integrand is the e to the 2 cotangent x. And it has the hallmark of an inner function, 2 cotangent x, inside the exponential. So we let u be the inner function, and then immediately, the very first thing we do is we take the derivative of that, but we write it in the differential notation because that's a nice way to do that. We look up on our table of derivatives, or remember that derivative of cotangent is minus cosecant squared. And then we compare. We say, okay, if we're planning to package this up as an e to the u, which this will allow us to do, can we convert everything else in the integral to u's, including the du? Well, this is almost what we've got, but let's match it up. And I always suggest that should be done in the sidebar before you go back to the main calculation. Just take that, divide by minus 2, and try to match everything that you actually see in the integral besides the main outer and inner part to what you've got here. Aha! So now we have a way to write exactly cosecant squared x dx as a du. Okay? And so now this integral is just going to be the integral of e to the u, which is certainly, just u, which is certainly easy, times a minus 1/2 times du. And I can just take that minus 1/2 out. It's a constant. Just e to the u du. And that is easy. Minus 1/2 equals minus 1/2 e to the u, that doesn't change, plus c. And that we just substitute back in. Oh yeah, what was u? It was an abbreviation for 2 cotangent x plus c. Okay. So why did this work? Again, it's because cosecant squared x was really close to being the derivative of what's inside here. And this notation is just a way to figure out, well, what else do I need to do to make this work? And it's a very standard notation that's incredibly useful to make this, this process of undoing the chain rule work.